this business of the energy story. So if you've got Chromebooks, phones, earbuds, just get that stuff put away. This is something, there's nothing on my this page about this yet. This will be posted when I'm done. And what I want you to think about is like skills, things that you should on a regular basis be doing, and one of those is taking notes. Like, many of you are going to go to college, and if you go to college and you can't write some stuff down, you're going to find yourself at a severe disadvantage. So regardless of like your other, like your status as a student, like you ought to be able to write some stuff down. So so here's where we are. We've got this idea that in certain engineered situations, mechanical energy is conserved, which means that at any one point, if we look at, for that engineered system, the gravitational potential energy, the elastic potential energy, and the kinetic energy, we add all those up, then what we'll find is that the total of those things should stay roughly constant over time. And we do lose a little bit of energy, like even in short amounts of time, to what we call thermal energy, even in a really well-engineered system. And that's like things heating up, that's things deforming, and there's really nothing we can do about that if we have a super duper, she's not here. If we have a super duper well-engineered situation, then it's not going to be perpetual motion, but it might be kind of close, like a pendulum, a really like well-built, sturdy pendulum with a, like a really light, strong cable and a really heavy mass. Those pendulums will move for a long time, just back and forth and back and forth, and that's kind of perpetual motion. Now, we're not going to get that with our systems, but over short amounts of time, our energy is largely conserved. And what we've been doing is just doing the math part of it, which essentially boils down to recognizing that we could have super complicated situations with lots of objects, which means there's lots of gravitational, elastic, and kinetic energy. There's like, things are moving, like there's craziness, but we're not doing that. We're looking at simple situations. And we're looking at what, for lack of a better description, might be called endpoints, which means we're looking at places where there's sort of a natural, well, this is where it started and this is where it ends. So for example, you hit the spring, object moves, comes to a stop up at the top of a ramp. That's what you did in the conservation of mechanical energy investigation. That seems like a really natural place. You start like with nothing moving in the spring, loaded. You end with this object at its furthest point. But what's really happening is there is no start and there is no end. At any instant, you can track energy, you can think about where it is, and you can think about how it got there. So what we've been doing is thinking about this in terms of like, well, let's say, so this is sort of a stage one thinking. Let's say there's no gravitational potential energy, there's only elastic potential energy, and that all gets transferred to ultimately gravitational potential energy. So we've got something like this, and then we make some measurements. And in a problem in the book or on the AP exam, they would say a spring with a spring constant of 820 newtons per meter is compressed, 2.5 centimeters. How high up above the ground can it push a 4 kilogram object, right? Like that's the book problem. We did the same thing. only instead of somebody telling us what all these things were, we measured them. We measured K by pushing on the spring, finding forces and distances, making a line of best fit, finding the slope of that line. If you don't know how to do that, then hear me, you have to be able to do that. I don't think everybody here can, but I think most of you can, which is good. Measure the compression of the spring with a ruler. We know the mass of the object, and then we can figure out how high up above its starting point it would get. And then there was an additional step for the activity that we were doing because we wanted to know how far along the track it would go. And that is related to how high up above the ground it goes, but it also depends on the angle. So there were two, we had an extra step, basically. So this is kind of tier one, recognizing that we can take a situation, simplify it, make some measurements or get some information, and find a number mathematically. And if you can't do those things, then work on those things. But there's another level to think about. And that second level is thinking about where energy is at any given time. And this is kind of turning it from a beginning and end, we don't care what happens in between, to recognizing that at any moment we could ask, where is the energy? This initial time and this final time are arbitrary. It makes a lot of sense for us to pick times that might be meaningful to us, but we don't know what's going to be meaningful in a different situation. If you've got a car on that's driving on a bumpy road, and you're an engineer and you're working on building shock absorbers, you don't care about when the spring is fully compressed. It's never going to be fully compressed. Nor do you care about when the spring has lost all its energy and the car is as high as it'll go. Those aren't your parameters. What you want to know is how tough do you need to build this spring so that your vehicle can drive on boulders at 20 miles an hour. And that is a really different question. So that's a really different type of scenario to think about. So for that, we thought about the energy buckets, right? And so what you can do is you can say, well, if we account for all of our gravitational potential energy and our elastic potential energy and our kinetic energy at any one time, then we know. Now, we can just sort of exclude thermal energy because we don't really have a good way of predicting it, but we know that if there's this much energy to begin with, there's going to be this much energy at every moment. So at some later period of time, maybe there's less gravitational potential energy. Maybe there's no elastic potential energy. What does that mean? Well, if I started with this much energy, and this much of it is gravitational, and none of it is elastic, then the difference must be made up by kinetic energy. So that's the second level of thinking about this. And this is a little bit trickier because what it requires you to do is be able to kind of freeze frame either in your brain, or if you are looking at something where you took a video of it, you could literally freeze frame and ask yourself, where is energy in this situation right now? And how did that compare to some previous stage? How might it compare to some future stage? And then the third tier, and this is what I want you to understand and be able to work on today, and it's going to be something where it sounds easy as I do it. What you'll find is it's tricky. It's really tricky. This energy is the ability to do work. Work is what speeds things up. So, and work is also a transfer of energy. So, at any time, if we have energy moving from one of these buckets to another one, that has to happen because work was done. And the way that work is done is not always the same. you might find that, sometimes this thing is pushing on this thing and work is done this way. Other times you have kind of similar types of objects and interactions, but the work looks a little bit different because maybe they're oriented differently in space, or maybe something is moving this way instead of this way. So you've got to be really thoughtful about how that energy gets transferred. In this case, we end up with less gravitational potential energy. Now that doesn't mean that, I'll give you some examples. But basically what that means is that ultimately, some of the energy that was here was transferred. Where was it transferred? I mean, in this case, it seems pretty clear that some of our gravitational potential energy was transferred, or even we could think about it as being transformed into kinetic energy. And our elastic potential energy looks like it was transferred as well. And what that means is that work must have been done. Work is going to be transverse energy. By pushing on things, so we've got a force over some displacement. So there has to be some force exerted over some distance. And this is where the energy story comes in. What I want you to be able to tell me is, first, where is the energy at any one time? That's relatively easy. The second is, if we look at 2 moments where the energy has been transferred, what did the work? There must have been forces. What forces were they? Those forces must have been exerted over some distance. So what was being pushed on? And I'll give you an example that's kind of complicated so that you can see what I'm talking about. So the example that we're going to use is we're going to have a ball that is on a spring. And we're going to think about it in sort of 3 cases. The first case is the spring is completely compressed and the ball is motionless. So this is like what we would normally think of as the starting point, okay? And then the second condition is going to be the ball all the way up at the top, totally motionless. And this is what we probably, most of us would think about as the ending position, okay? And, the third case that we're going to think about is the more interesting one. And that is, what happens when this ball comes back down? And it hits the spring, and it squishes it. And if this were a perfect system in which mechanical energy were perfectly conserved, the spring would ultimately squish all the way back down. But that's not what we're going to look at. We're going to look at what happens as this ball comes back down and squishes the spring, but it's not all the way down yet. Okay? It will be, but it's not all the way down yet. So here's our system. We can think about it like this. We have a ball. It's resting on a totally compressed spring. Okay, and then so that's our starting scenario. The next scenario is the spring is released, and the ball is all the way up above the ground, and it's at its highest point, which I hope you remember means it's going to be momentarily motionless, right? So you can picture what this is going to look like. If this perfectly conserved mechanical energy system, this could be a perpetual motion machine. The ball would just keep going, landing, the spring would squish exactly the same amount it squished before, it would go just as high, it would just go up and down and up and down and up and down for till the end of time. But that's not what we're interested in. What we're interested in is this scenario right here. You've got the ball, and it is coming back down. So it's moving with some speed toward the ground. It hits the spring and compresses it, but it's not all the way compressed yet. So the ball is still moving down. Our spring has compressed a little bit, but not all the way. This is the scenario that we want to look at. So there's two things that we need to do in order to tell the energy story. The first is we need to identify where the energy is. And we have two time periods that we're looking at here. So where's the energy here? Where's the energy here, right? Like two instants in time. So let's look at that. Here, our ball is not yet down to its lowest point. So there is some gravitational potential energy. There's not as much gravitational potential energy as it was up here, though. Like there was a lot up here, there's less here, but not zero. So there's some gravitational potential energy. This situation, I told you that it's hit the spring, but it hasn't yet started to squish. So there's no elastic potential energy. And the ball is moving. It's moving actually as fast as it's ever going to move. As soon as it starts hitting this spring, not necessarily as soon as, but pretty close after it hits the spring and the spring starts compressing, it's going to start slowing down. So our kinetic energy is pretty much maxed out. It depends on how strong the spring is compared to the force of gravity. There will be a short time during which this ball will continue to accelerate downward. But as the force of that spring increases, it will equal and then exceed the weight of the object. All right? So this is our starting energy. And then our ending energy, well, it's lower. So it has less gravitational potential energy, but it's not zero yet. So we have less gravitational potential energy. There is some elastic potential energy now. It's not maxed out. And our ball has slowed down, but it hasn't stopped yet. Okay. So the question is, how did this energy get moved around? In order for energy to be transferred, work has to be done. So what are the forces here, and what's the work that's being done? There are, like, you can kind of think about it in a whole bunch of ways, but what I like to look at is I like to look at something like this. This kinetic energy decreased. So something transferred kinetic energy out. The gravitational potential energy decreased. So something transferred that gravitational potential energy out. Well, what was that? What were the forces that did that? What do you think?
The ball interacting with the spring.
Okay. So the ball is pushing, it's got to be like, ball is pushing on the spring. We know that, right? The spring here is not experiencing any forces yet, which is why it's not squishing. What makes the spring squish, now a lot of times we're like, well, it's gravity, because we think, well, the ball is being pulled down by gravity, so that's what's ultimately squishing the spring, but not really, because gravity was present here too. Gravity was present here. Gravity isn't what's making the spring squish. It's the ball. So one of the things that's happening is that we have kinetic energy being transferred into elastic potential energy. So the ball is pushing on the spring, so the ball pushes on the spring, transferring energy from kinetic energy to elastic potential energy. What's the force? The force is the ball. The ball is pushing on the spring. So there's our force right there. If the spring didn't move, there wouldn't be any energy transferred. So this is happening as the spring squishes. So there's our displacement. So we've got a force, we've got a displacement. We could think about the amount of work that was done to store this energy in the spring. It would be force times displacement. We know that that springs exert varying forces. So there would be, so to a certain degree, this would be a little bit difficult to calculate because the force wouldn't be constant, but we could relate the force with which the ball is pushing on the spring, with which the spring is pushing on the ball. Because of Newton's third law, we know that the force from the ball on the spring and the force from the spring on the ball always have to be the same. Because of Hooke's law, we know that the force from the spring is always going to be 1/2 kx squared. So actually we could quantify this whole thing as 1/2 kx squared, where this is x. The amount of work the ball does to the spring has to be equal to 1/2 k times x squared. Has to be. That's how much energy is in the spring when it's squished this much. What put the energy in there? The ball. Where did that energy come from? Kinetic energy. So the ball's kinetic energy would have decreased by exactly this amount. If we looked at 1/2 mv squared here, and we looked at 1/2 mv squared here, we will see that it would have changed by exactly this amount. Okay, then, so you can see what I mean. It's like, it's a little confusing. The math is there, but this is really a different thing conceptually, okay? And then there's something else happening here too, because we have gravitational potential energy that has decreased. And how is that, where is that going? And it turns out this is even more complicated, luckily for you, because here's what's happening. We want to look at this and be like, well, the elastic potential energy is increasing. So the gravitational potential energy is being transferred into elastic potential energy. That makes sense. But how would it do that? There would have to be a force. And that force would have to be exerted over a distance, Mikey. That force would have to be exerted over some distance. That means that gravity, the force of gravity, would need to be pulling on this spring. And it is, but not much. We're kind of thinking about the spring as if it had no mass at all, really. So we are not getting energy transferred directly from gravitational potential energy to elastic potential energy. The force of gravity isn't doing any work on this spring. So what in the heck is going on? Here's what's going on. Remember our gravity spring? There's a spring that connects our ball to the center of the earth, conceptual spring. That spring is doing work. What's it doing work to? What is the gravity spring pulling on? What does it look like it's pulling on? The ball. The gravity spring is doing work to the ball. Gravity is causing the ball to speed up, or is tending to cause the ball to speed up. So what's really happening here is that gravitational potential energy is being converted into kinetic energy in the ball, right? Yeah, isn't it elegant? And that is being converted into elastic potential energy as the ball does work to the spring. The ball never speeds up, right? Like once the spring gets squished a little bit, the ball isn't really speeding up. But if we switched off gravity, it wouldn't squish the spring as far, because gravity wouldn't pull the ball down as much. So the force of gravity is doing work on the ball to increase the ball's kinetic energy. And the ball's kinetic energy is what is ultimately being transformed into elastic potential energy. So that would be the second part over here, which is that gravity pulls on the ball, transferring energy from gravitational potential energy to kinetic energy as the ball moves down. Here's our force. Gravity is pulling on the ball. Here's our displacement. The ball is moving down. How much energy gets transferred? We already know. It's going to be mg delta h, which in this case would be mgx, because we already said that this change is x. This is how much energy gets transferred into the kinetic energy of the ball. It's going that much faster than it would have been going without gravity. And that ultimately is getting transferred into elastic potential energy as well. And this is the energy story. We have kinetic energy getting transferred, we have gravitational potential energy getting transferred. As that ball squishes the spring all the way, and then it starts going back up, we're going to start to see some of the opposite things happen. And so this is where, remember I said, like, we can have the same situation, different energy story, depending on like when it's happening. Imagine now this ball squishes the spring all the way, and then starts moving back up. If it gets to this point right here, now it's moving up. Now, elastic potential energy is getting transformed into kinetic energy and gravitational potential energy. It's like the flip side, just because the ball is going the other direction. And learning to think about it this way is really cool, it's really fun, it's really challenging, but I have confidence that you all can pull this off. So here's the plan.